Unit 3, Lesson 7 is a study of why we want to know how to solve these equations. How do they show up in the physical world? So, alright, let's take a look. Here's a linear second-order non-homogeneous equation. And one of the examples of how this appears in the real world is motion on a spring, or for that matter, I'll say a spring, but really it could be any vibrating object. So, I'm going to refer back to this picture here. Consider a mass M suspended on a spring from a fixed vertical support. Let L sub 0, this length, be the natural length of the spring. When a weight is hung on the spring, it extends the spring an additional amount L. See? L0 here, L here. Where it rests in equilibrium position. According to Hooke's law, the tension on the spring is directly proportional to the length of the extension. So the force is a proportional constant times the length of the extension. And this force would be the same as the weight of the object added, which is its mass times the gravitational constant, whatever that is. Therefore, our KL is mass times gravity, from M, the mass of the object, and G, the gravitational constant. Now suppose at some fixed time t sub 0, the mass is displaced y sub 0 units from its equilibrium position. So in other words, we pull it down an additional y sub 0 units or something like that. Then if y equals yt is the distance of the mass from equilibrium, that's this length right here, at time t, then the extension at time t would be the natural extension plus yt, the extension from this force. Note the downward direction is usually considered positive, so think of this, it'd be natural, this is a positive number, this is a positive number, and if we went backwards it would be a negative number, but the spring problems work identically in reverse. If they become, instead of springs, like shock absorbers or something like that. Okay. According to one of Newton's law of mechanics, the rate of change of downward momentum is equal to the net downward force. So in mass symbols, the rate of change of the downward momentum, which is the mass times the velocity, which there it is, m force equals mv, equals the net downward force. Well, that would be the weight minus a constant times the extension plus y of t, whatever y of t is at the time. But since our mass times gravity is k times L, put KL in here, and it'll subtract off with this KL. What we would have is this differential equation, the second derivative of the function, and by the way, I also divided by m, equals some constant. Of course, if I divide by m, it's still another constant, times y of t. So then we would actually have this differential equation to solve. Second derivative of a function plus some constant times the function is equal to 0. And we've already done these. So this solution would be C1 cosine of square root of k over mt plus C2 sine of square root of k over mt. Right? Because the characteristic equation is m squared plus k over m equals 0. So that's something we are good with.
Oh, I see.
Okie doke.